Welcome. Today we're diving into the powerful science of statistics, and we're going to do it by looking at a question where the answer is, quite literally, a matter of life and death.
So let's get right into it. We're going to explore a really fundamental question. How do we separate what we hope is true from what the evidence actually tells us? And we're going to do it by looking at a super high-stakes medical breakthrough and see how statistics is the tool that helps us get to the truth. Okay, so picture this. It's the early days of heart transplants. This was the question on everyone's mind. You had these incredible, miracle stories of individual successes, but was that the whole picture? We're going to use this exact real-world problem to see how statistics gives us a solid framework for finding answers we can actually trust.
Right? So how do you get from one powerful, emotional story to a conclusion that could potentially save thousands, maybe even millions of lives? Well, that whole journey, from just a hunch to solid evidence, it always starts with gathering the clues.
And that brings us to the data. This is always step one in any statistical investigation. Seriously, think of it like gathering the raw clues for a crime scene. The fingerprints, the witness statements, all the stuff you need before you can even begin to solve the case.
Okay, so take a look at this. This is a little snapshot of data from a real study. It's pretty straightforward. It tracks two groups. You've got the treatment group. These are the folks who got a heart transplant. And then the control group, who were similar patients but didn't get one. And the main thing they're tracking? It's simple. Survival, measured in days. Now, this part is so important. How we collect this data totally changes how strong our conclusions can be. See, in what's called an observational study, we're basically just people watching. We just watch what happens. But that can be super misleading, right? For example, what if only the healthiest, strongest patients got the transplant to begin with? Of course their outcomes would look better. That would totally skew the results. On the flip side, you have a designed experiment. This is the gold standard. It uses randomness, like a coin flip, to decide who gets the treatment. This is how you avoid that bias and get much, much stronger evidence.
Okay, so having data is a great start. But a big list of numbers, it doesn't really tell you a story on its own, does it? It's just a jumble. We need a way to make sense of it, to find the signal hidden in all that noise. And that, my friends, is where a statistical model comes into play.
Think about it like this. A model isn't reality. Not at all. It's more like a simplified blueprint for reality. It's basically an assumption we make about the process that created our data, kind of like trying to figure out the hidden rules of a game you're watching. So for our heart transplant case, a model is just a way to describe how patient survival might work, with the transplant versus without.
All right, so here's the more textbook definition, but don't let it scare you. All it really means for our heart transplant problem is that our model contains two competing theories. Theory 1, the transplant does nothing for survival. It has zero effect. Theory 2, it does have an effect. Our whole goal is to use the data we collected to see which of those two ideas holds more water.
And now, we get to the climax of our story. This is called statistical inference. This is the part where we take our blueprint, our model, and we hold it up against the hard evidence from our data. This is the moment of truth. So, when we crunch all the numbers from the study, the result is, well, it's pretty striking. On average, the patients who got the transplant survived 263 days longer than those who didn't. 263 days. On the surface, that sounds like a home run, a massive success.
But here's the million-dollar question. Was it real, or was it just a fluke? See, in any study, there's always an element of randomness. Maybe the treatment group just got lucky, How can we be sure that this huge 263-day difference is a real signal telling us the transplant works and not just random static, just statistical noise? This right here, this is the core problem that inference was invented to solve.
The way this works is actually a lot like how a detective thinks. It's pretty cool. So, step 1, you start by assuming innocence. In statistics, we call this the null hypothesis. Basically, we pretend for a second that the treatment has absolutely no effect. Step 2, you look at the evidence. You ask yourself, okay, if this transplant really did nothing, what are the odds we'd see a survival difference of 263 days, or even more, just by pure luck? And then, step 3, you make a call. If that probability, that chance, is ridiculously low, then you throw out your no effect assumption and you conclude, nope, something real is definitely going on here.
So, what was the final verdict? What did our statistical investigation find? Did the evidence we found make that initial no difference assumption look, well, totally ridiculous? Oh yeah, big time. The analysis showed that the probability of seeing a survival difference that big just by random chance was tiny, like incredibly small. And that provided powerful, concrete evidence that the heart transplant procedure was in fact saving lives.
And this right here, this brings us to probably the most important takeaway of this whole thing. Statistics doesn't give you absolute certainty. It never ever says this is 100% proven, case closed. What it does do is give us this incredibly powerful method to measure our evidence and deal with uncertainty. And that lets us make much, much better decisions based on what we actually know. And that whole process we just walked through, starting with a question, gathering data, building a model, and then doing inference, that is a powerful engine for discovery. It's used absolutely everywhere, from medicine to economics to, well, you name it. It's how we navigate a really complex world, by helping us separate what we hope is true from what the evidence is actually telling us.